All right, as promised, we are going to be We're going to be solving the Schrödinger equation for a particle in an infinite square well. So in the last video, we derived the one-dimensional time-dependent Schrödinger equation, as you can see here. And even though it is a one-dimensional system, it is still a fairly difficult differential equation to solve by virtue of the fact that it is a partial differential equation. And we're not currently in the business of solving those quite yet, so we're going to have to sort of massage this equation into something a little bit more manageable, something more closely resembling an ordinary differential equation we're all good and familiar with, I hope. But if not, maybe I can make a video on it, on how to solve certain differential equations. But for now, we're just going to solve this one, and I'm just going to go off of the assumption that you've had a little bit of background in ordinary differential equations. But I'll try to be as clear and concise as possible for those who haven't. So, nevertheless, we are going to be solving the simplest case for now. Okay, so what we need is to sort of work this into a differential equation, an ordinary differential equation, and remove the dependence upon the potential. So we want the potential to be zero, but we also want to keep the particle that we are observing, that we are trying to describe, contained within its infinite square well. Okay? That means the potential, when at these boundaries, if the particle were to collide with these boundaries, or even go beyond it, well, the potential would be equal to infinity. Okay? Okay? So that's what we need to ensure, and we need to establish these boundary conditions. But we also want to, once again, remove the dependence upon the potential altogether here. And to do that, we are going to make a little bit of a caveat. So our potential, so to keep the particle from permeating the walls, we are going to ensure that it is infinity whenever we have a particle that is less than or equal to less than or equal to 0, and then greater than or equal to L. Okay, so to keep the particle contained within these walls, this is our first boundary condition. And to remove the dependence upon the potential, we are going to ensure that it is 0 whenever it is greater than 0 or less than L, or the length of the box. Okay? So this is our first set of conditions that we have to work. So now we can further rewrite this equation without the dependence upon the potential here. Okay? So to do that, we just remove it. And in addition, we are also going to be removing the dependence upon our time variation. If you recall from my last video, the time-independent version is just this. So we're going to have the total energy, or our eigenstate energy. So this is going to be dependent on x, is equal to minus h bar squared over bar over 2m, where we now no longer need a partial derivative. We can just write d squared sine x over dx squared. Okay, cool. That's definitely more manageable. Now, I want to point out another close distinction that needs to be made here. Now, we have two different kinds of psi characters that we need to draw some distinctions for. And the psi that we're using is referred to as our Eigen Function. And I briefly touched upon this before, but what we are solving for is the wave function, and these aren't necessarily the same thing. So the wave function, well, actually rather the Eigen Function, is just this. Okay, so this is our eigenfunction, but the wave function that we are looking for is more of a capital psi. It's a little bit more regal, right? So this is our wave function, and our wave function has the dependence on x and t. And this is going to be equal to our eigenfunction, which has a dependence on x, and we are multiplying that by e raised to the negative I e t over h bar. Okay? And if you're a little bit confused about where that comes from, I can show you one thing. I'm not going to do it all for you, but it's pretty easy to derive. You were just separating these characters out before. You recall the wave function I described previously, which is just I times kx raised to the I kx minus omega t. Well, all this obviously looks different than this portion of the wave function here, but I assure you it's equivalent, because if you were to just plug in the momentum, which is equal to h bar k, and then take your energy, which is equal to h bar omega, well, you just solve for omega and k, plug them in, and you'll see that these separate very nicely. So with that in mind, we can sort of get rid of this, but if you want to do it to soothe your own sort of conscience, or if it helps sort of take off a little bit of the concern there, by all means. But for now, we're just gonna keep going. So now what we have here, we need to sort of rework, okay? So we're gonna solve for our second order differential equation here, all right? So we are going to move this all over to the other side. So we're gonna have d squared psi of x over dx squared, which is equal to, now we're bringing these over, and we're gonna have 2me, remember this is negative, over h bar squared times psi of x. Okay, so this looks a little crazy still, but we're going to make a substitution here. We're going to say that k squared is equal to 2me over h bar squared, okay? So this is 2me over h bar squared, right? And if we were to obviously just solve for k, it would just be the square root of that, right? So we can now just plug this bad boy in over here, okay? So you'll see that this makes solving the differential equation more manageable if we make this substitution, since we're just now only working with one variable. Okay? So we're going to have d squared psi of x over dx squared equals minus k squared psi of x. Alrighty, so now what we are going to do is we are going to bring this all over here, and we're going to have d squared of psi of x dx squared plus k squared psi x equals 0. Now, if you've had some experience in differential equations, all we have here is a linear, homogeneous, ordinary differential equation. Pretty easy to solve. All we really need to do is bring out the old characteristic equation. And the characteristic equation is going to be lambda squared plus k squared equals 0. And we basically just solve for lambda. Sometimes you would use the quadratic formula, or you do some factorization, whatever, but fortunately we don't need to do that. We get to deal with the complex numbers. And that will give us lambda squared is equal to minus k squared. And then working that out, we have lambda equals plus or minus ki And this is what we're going to be plugging in to our general solution, okay? So for our general solution, now I could just go straight to the actual solution without sort of like going through the process, but I find that to be a little bit confusing sometimes. So I'm just going to start out with that general and then sort of work our way over there. So we know that there are going to be some coefficients, and we're going to have to plug this in to our exponentials, okay? So what we have now is psi of x is equal to our some particular constant, right? So we're gonna just do C1, where we have e raised to the k I x. All right, and that's gonna be plus C2 times e raised to the minus, oops, since we have our conjugate pair, we're going to have to use our minus kix. All right, so this is cumbersome to go through. I just find it very helpful and instructive. But you could obviously go to the very end, which I will include a link if you don't want to see me go through all this little tedious algebra. But that being said, this is what we're going to do. We're going to have to invoke Euler's identity, which will mean that our psi of x is equal to our C1 times, okay, so ikx is going to be cosine of kx plus I sine of kx. And then, again, we are going to have to do the same thing for this side, and that's going to be plus C2, where we have cosine of, since there is a negative, it's fortunate that cosine just absorbs the negative, so we're just going to have cosine of kx. But sine, we can bring that negative out, and we have minus I sine of kx. All right, so now we can sort of manipulate some of these and put together our like terms. Actually, rather, let's put together our cosine terms, which will mean that we have this equal to C1 plus C2 times cosine of kx. And this is going to be added to, now we're going to have C1i plus C minus, actually not plus, excuse me, minus C2i times sine of kx. Okay, so all these factors all these coefficients in front of our trig functions, all they are just constants. So we can just assign some arbitrary dummy variable to represent what these are. So thankfully, we just call this A, this will be A, and this will be B. Okay? So this is what we're going to be working with now. So we're going to have psi of x is equal to A times cosine of kx plus sine, oops, that was B sine, my bad. So that's going to be B times sine of kx. All right, so we're making some progress. We need to sort of massage this equation a little bit more, and that will only be possible if we establish some more boundary conditions. So beyond this barrier, we are dealing with the Eigen Function equal to 0. Okay, so this has to be true because otherwise this wouldn't exist if it were to be outside of the box, because you're talking about a potential of infinity, and that would be undefined. So the Eigen Function is going to be equal to 0, and we can say that because of this, we can have our Eigen Function where x is equal to 0 must be equal to 0. Pretty easy. And then similarly, we have to establish the same condition at the point L in the box. So we're going to have our Eigen Function where x is equal to L must necessarily be equal to 0. And now we can use this to sort of work this problem out here. Now, let's start out with our first condition. So if x is equal to 0, well, we're going to have 0 equals, okay, so cosine of k times 0, well, that's just 1. We're just going to have a plus, well, b sine of k times 0. Sine of 0 is just 0, so that's just 0, meaning a must be 0. So that sort of simplifies our equation now. So all we're left with is psi of x is equal to b sine of kx. Okay, so now we can impose this other condition where now 0 is equal to, what do we have here? So we're going to have 0, which is equal to b times sine of KL. All right? B times sine of KL. And this b we can sort of remove. We can divide that out, and that will just be now sine of KL. Okay? Since x is equal to L with this condition. So we can actually just take the inverse of sine. And what we have, we'll do this over here. We're going to have KL is equal to sine inverse of 0. Now, where is sine equal to 0? Interesting. So let's just sort of illustrate this with a little bit of a diagram where we have our sine function starting at the origin. Okay? So at 0, it is equal to 0. Okay? Well, we don't want that part of this condition here to be 0. And that is due to the fact that we need the particle to remain in the box. Otherwise, if it was 0, well, then that would indicate that the particle just vanished, and that violates a lot of conservation laws. So right here, sine would be equal to 0. Well, sine of pi would be equal to 0. And then similarly, sine of 2 pi. And then sine of 3 pi. And so on. Okay, so this is the condition that we have to impose. So that would mean that our sine here would be equal to n times pi. So even or odd integers, this could go both ways, but we're sort of kind of containing this in a positive region for now. So n can take all values from 1, 2, 3, and so on, and this condition will hold. So KL is equal to n times pi. All right, and we can solve for k here, and k is equal to n pi over L. All right, so we can now take what we had in our general solution and plug our k factor back in, and we just have psi of x is equal to b, our coefficient, or sine, is n pi over L. Okay, so this is our general solution. This does tell us a lot about the system, but there's also another way of representing this solution. You can represent it in terms of the energy, because if you recall, this condition we can now plug back in here. So K And we obviously know that k is equal to the square root of this. So we are going to have the square root of 2me over h bar squared, which is equal to n pi over L. And what we want is to solve for our energy here. And our energy will be equal to, let's see here, we got n squared, pi squared, then we're going to have h bar squared over L squared times 2m. And this is one of the solutions that we can use to represent the fact that this shows us that the particle's energy is discretized. And in fact, this also illustrates that the ground state of our particle is in fact non-zero, meaning it has no mode to represent it, which would sort of look something like this as our ground state, and that's known as the 0 point energy. And we'll maybe take a further deep dive into that concept in a future video, but for now we're going to leave it at that. In the next video I'm going to be normalizing the wave function, solving for this b, this coefficient here, and then we're going to get a more visual representation of how this solution looks like. So thank you for watching, stay tuned, and please remember to like, favorite, and subscribe if you want to see more videos like this in the future. Thank you so much.